Hello, everyone. My name is Igor Nakhvat, and today we're going to talk about optimization. During this talk, I will cover storage and compute optimization on Amazon EMR infrastructure that helped to decrease almost $1 million during a year. Let me do the quickly self-presentation. I'm lead software engineer with more than 10 years of data engineering experience. I've started my career working with a single Oracle DB instance. The physical machine was located in the same office. It was like 20 meters away of my desk. Then I switched to on-premise Hadoop cluster. It wasn't located in any cloud. It just was a huge data center, and it takes months to buy and install new hardware for the project. And now I work with the multi-cloud solution. Our optimization presentation, we will start from the use case, where we'll describe the technology, infrastructure, and so on. We're going to talk about batch processing. So it's like a pretty standard use case where we have different data sources. The main one is Amazon Kinesis, the message broker. Almost all data comes from this resource, but beside Kinesis, there are a number of relational and non-relational resources. In relational resources like Postgres, there are some financial data like transactional, and Mongo contains different collections. All this data goes to Amazon S3 through the ETL process, so all data is stored on Amazon file system. And there are two main processing languages, technologies, frameworks. The first one, this is Hive, and the second one is Apache Spark. These two execution engines are used to populate the data marts based on the raw data on Amazon S3. So both engine looks on the file system directly. And data marts is used by analysts, by visual reporting, which is Tableau. So some dashboards are used by managers who don't have access to Hive or other SQL engines, so they use Tableau. And there are also analysts who can work both with Tableau and raw data in data marts. In general, there are more than 10 engineers who support the current infrastructure, ETL, all engineering stuff. And there are more than 20 analysts who create data marts and use infrastructure as well, and more than 100 the end users who can only view Tableau. So that's our test case. As I mentioned before, the optimization consists of optimization strategy consists of two main parts. Storage and compute, and we will start from the storage and using features that are provided by cloud provider Amazon. Any talk about optimization, storage optimization, we need to start from intelligent tiering. This is the great feature from Amazon, and each project that utilized S3 should use this feature. For our case, everything was fine with that. This feature was switched on. As you can see at the graph, you can see the distribution that the expensive standard storage, the data volume in this standard storage is relatively small. So almost all data sits on intelligent storage, which is cheaper than the standard one. And the good thing that Amazon does, it all transition in the background, so we don't need to worry about it. Also, you can see this blue text. The case was more than a year ago when Amazon implemented new archive storage, and it automatically pushed the old data there, which also was really nice. You will not find on this graph Glacier, which is like cold storage. This cold storage is even more cheaper than archive one, but on the other hand, you can't read the data immediately from this storage. For some cases, it can take more than 20 hours to get the data from the cold storage, so it's not accessible instantly. And for our case, we decided that it's better to drop the data or store it as is on intelligent steering rather than moving it to Glacier. But for some cases, Glacier can be a good option also. Next topic is lifecycle configuration. It should be applied for where possible. The good candidates for the lifecycle configuration is intermediate data. It can be some staging files, logs. I believe no one needs any kind of logs older than year or even months. For our case, months is more than enough to store the logs. So everything that we don't need to store forever. For this particular case, I have created more than 60 separate lifecycle policies based on S3 prefix. There are also ways to utilize tags, so you can tag your data on S3 and then create configuration based on tag. But anyway, it's also very nice feature to get rid of unused files automatically. Next feature is bucket versioning. It's a good way to have a possibility to restore the data if it was deleted by accident. But on the other hand, this feature is not free because you need to pay for all the previous versions. That's why for our case, we created the bucket versioning, but only for 3 days. So if you drop something, it is possible to restore the data during the next 3 days. But then lifecycle will wipe it out. So if you use bucket versioning, make sure that there is correspondent lifecycle policy, because for the most cases there is no sense to store the previous versions forever. So sometime they need to be deleted after some time. And that was it regarding the built-in function. So let's talk about something more interesting, which will be new information for you. This is optimization using custom approaches. Again, I will start with like common and well-known topic, but I can't ignore it. This is data formats and compression. If we store data as a plain text, we have a good possibility. So a good possibility to optimize it. For This particular case, all data were stored by Parquet Snappy. On the graph, you can see the same file. This is parking violations that was stored with different data formats and compression. And you can see there is distribution of some compression is better, some compress better, but it takes more computing resources to read. And there are other cases, but in general, Parquet Snappy is a good compromise between the volume on the disk and the resources need to be read. So again, make sure that you use the right format with compression, so you don't store data in a plain text. So let's talk about the first good use case about the unused tables. Meet Alex. Alex is data analyst. He have been working at our company for the last 2 years, and he did a great job during this career. He has created 15 dashboards at Tableau. There are about 100 separate tables in his personal schemas with ad hoc, some aggregates, so with some used data. But then, after a while, he decided to quit the company and became a musician. What does it mean for us? If our offboarding process in our company poorly defined, and actually, me personally, I didn't have a chance to see like perfect onboarding process. We can have an issue with unused object. On the top right corner, you can see a real example of personal schema for a person who left the company. And I found about 3 million separate files in his personal schema with almost 200 terabytes on Amazon S3. For the company, storing such data cost almost $10,000 per year, and this data is used for no one. So it's like deprecated data. And our goals as data engineers to get rid of such issues, we can do it in 2 ways. The first way is more managerial, so we can define the process properly, set up some kind of system, or alternatively, we can do it into engineering way, because there is a way to find such cases without even knowing that person has quit the company. There are S3 access logs that can help us to find the files that were used for no one. And also we can cover the next case. This is unused tables. For example, when the business logic is no longer valid or used by someone, we can have a dashboard in Tableau that is no one view. For example, in Tableau, you can see the number of views for each dashboards. And for example, if you find a dashboard that has 1 view per month, it is a good way to raise a question: do we need at all these dashboards? Probably the logic is incorrect, or the person who has created this table got a promotion and he no longer needs this data. So there may be a lot of options why do we need this object anymore, but it can be an issue, especially when our project lasts like 5 years. So it's pretty huge period to accumulate such branches of unused logic, and that here we can do our job, data engineering job, and find such objects, review them, and delete them. Other case regarding the files, this is orphan files, and under this term orphan, I mean files on our file system. This is S3 or HDFS without any metadata in Hive metastore. So, for example, we have a bucket, and in our buckets, all data have metadata in Hive metastore because we use relational tables to read the file. So if we don't have any metadata in metastore, that means that we need to delete these files. The ways where these orphan files can arrive, it can be using external tables, and if we delete external tables and do not clean location manually, the data will sit there forever without any chance to be read from the SQL engine. And also this is staging data, temporary data. We can apply lifecycle rules, as I have mentioned before, and also S3 access logs can help us to define this object. For the orphan files, I have created a custom Spark job that reads the data from Hive metastore. On the other hand, it reads data from access log, and it combines the two data sets, and it shows the difference. So I can find such orphan files and delete them later. So to do a quick summary, use intelligent steering is like the must option. Create lifecycle rules where possible, use data compression, and create a framework that will help you to find unused tables, data orphan files, and wipe it out. This is the real example after the optimization that took almost a year. Here you can see the graph. The blue line shows the total size in petabytes. There is no distribution between S3 tires, so I have combined all tires all together, so it's cumulative data size. And you can see the huge drop here at May, where lifecycle rules were applied, and the first way of finding and eliminating unused tables and orphan files were made. And also there was a second wave on finding and deleting the unused files. As you can see, during the year, our data warehouse get rid of 3 petabytes. So the incoming data volume's still the same. So here you can see from May till November that data is growing, but we have deleted more than arrived, which is also a very good result. Here you can see the most, I believe, interesting part. This is cost. So it's not about data volume, it's about the real money. I have blurred all numbers, but each point for each month stand for X million dollars. And you can see that the cost goes down during the life cycle rules, unused tables here and here, but there are also a very huge impact that were made by Amazon S3. It has provided a huge discount, so the all cost for all tires in our region went down. So that's why there is a big drop on the graph. And on December, we have also a very huge drop down because of implementing new archive storage. It was really hard to define the ratio because during the same time we have deleted a lot of unused tables, logs, and so on. But in general, December is 36% cheaper than January, which is also a great result, and we can see that the trend line goes down. So that was about the storage optimization, and we can move on to the compute optimization part. This part, I would like to start from the physical infrastructure. If your project is old enough, there is a high chance that Amazon released the newer version of EMRs, and newest version allows you to use next generation of EC2 instances, and always this new generation are better than the previous one. They have more CPU, more memory, and they cost less than the previous one. So the first step is to get the latest version, upgrade your instances to the latest available generation. This is a good starting point. Next one is logical organization. For this particular case, I have distributed the workload across 3 main clusters. Before, the workload were distributed like randomly across even more clusters, but there were no logic at all. So I have selected 3 main clusters. The first one was only for hourly jobs, and for our case, we have hourly jobs that are running during the whole day. So it's each hour we have something running, and it's pretty flat workload. It's very predictable. The next cluster was designed for the daily workload. It's only for daily jobs and takes about 15 hours to calculate all the data marts for the last day, and we don't need to have a huge cluster for the rest of the day. And the third cluster, I called it heavy. I've redirected there only few jobs. As far as I remember, it's only 5. And these jobs are pretty unique. They run one by one, not in parallel, consequentially, and they consume all available resources, and it's pretty slow. It takes more than 2 hours. And I've decided that it will be better to run them on a separate cluster so they can't interfere with daily and hourly workload, and I can apply different lifecycle rules and scaling. So this is our next topic. There are 2 main options regarding the scaling in EMR world. The first one is custom rules. So you can define a rule based on various options like free memory, number of containers, and so on. The good thing about the custom rules is that you can tune them very precisely, and this is the best option for some edge cases. But in general, they are more harder to set up. And if you did wrong configurations, for some cases, instead of decreasing cost, your bill will be increased. And the next option is EMR managed scaling. It's easy to set up, best for the general purpose, but again, for some edge cases, it can be worse. For our case, I have created the custom rules. As I have mentioned earlier, we have 3 clusters: hourly, daily, and heavy. For the hourly cluster, I did not set the scaling policy because the workload was flat. But for the daily, I have provided scaling out policy based on available memory. So as soon as the percent of available memory is less than 15, we're going to add extra portion of free nodes. And as soon as there are no more application, we are going to aggressively shrink down our cluster, because we know that daily calculation has been ended, so we don't need to keep resources anymore, and we can quickly squeeze it. Almost the same options were granted for the heavy cluster, but in this case, we need a lot of resources immediately. So as soon as any application arrive to heavy cluster, we want, 400 nodes to be available. So very aggressive policy when we have at least one application, and when there are no more application, we don't need the resource, and we can shrink our cluster back. The next part is spot nodes. Spot nodes is a good way to pay for the same instances less, but there is a risk that Amazon will borrow it for you back. So here at the graph, you can see the frequency of interruption. There is a separate page on Amazon documentation where you can see this rate for the different instance types. As you can see here, our best option is M5D because the chance of interruption is less than 5. And we probably should avoid D2 instances because the chance is too high. I've started testing spot node ratio from 20%. So 20% is spot nodes, and the rest part is a standard on-demand node. But the cluster worked not so stable, so that's why I've decided to reduce the number of spots nodes to 10, which has worked fine for hourly and daily. And for the heavy cluster, I've decided to leave it without the spots nodes because the price of interruption is too high, and it's better to ignore this risk at all. So once again, spot nodes is a cool feature, but you need to test it for your particular case because sometimes reliability is more important than the price. Here, let's talk about the compute optimization results. On this graph, you can see the daily trending. So this line shows how much all EMR cluster cost for one day. I have also blurred the cost. It's not millions, it's $1,000 per each day. And there are also 2 lines. The first line, it's like the blue one. This is our baseline. So it's like situation that we have right now. And the green line, it's X. This is our goal. So our goal is to push the daily trending graph below this X level, so we can save more money. The main line is not flat because of auto-scaling rules. You see that sometimes it goes up or sometimes it goes lower, and it's hard to define like the base layer. So I have choose one 7 days window in April, and I have calculated the amount of money that we pay for this 7 days window as our baseline. So all savings in percent, they will be calculated based on this period. And this is our picture after all optimizations. Here you can see the same green line. It's our goal, X dollars per day. And you can see that the graph went below this line during the same 7 days window in a row. That means that our approach works really fine, and this is like the real results from production data warehouse. In general, the overall costs reduced by 60% with no negative impact on ETL. So data team provides the data into the same constraints, but company pay less for the same result, which is really good optimization. In this presentation, I didn't mention EMR serverless. This is a relatively new feature from Amazon. They have invented it probably a year ago, so it's pretty new. And this is our plans for the future to try out serverless, and it seems to be it can be even more effective than the previous approach when you need to create separate clusters. So it's like plan for future, and for you it's also a good topic that you need to keep in mind as an option that can help you to save the money. And that's it from my side, so we can move to the questions.
Yeah, thank you, Igor, for this interesting topic. Yeah, a lot of material. So also we have questions. So maybe first about those S3 optimization. So you mentioned about this artificial intelligence tier, and does it mean that I should always use this AI tier, or are there any cases when I should use standard tier?
I believe if we're speaking about the project that relates to data storage, so it's not like some content delivery network or I don't know a web application where amount of data is relatively small, but we need to get the data really fast. Then I would say that this intelligent tiering is a must feature for any project that relates to data warehousing, because we have a lot of data and it's fine to wait extra 1 second or 1 or 2 seconds to get the results. So it's good balance. You pay less, but you wait more. But in our world, 2 seconds is fine. If we're speaking about ad hoc analytics, so it's not something that connected to online processes where you need to keep low latency. So if the latency is not a problem for you, then yes, intelligence tiering is must-have feature.
Mhm. Also, you mentioned a lot of information from different for different AWS resources, but are there any advisor in AWS that can help to reduce costs?
Mm, you know what? The for that particular case, the heaviest part was connected to monitoring and inspecting the data warehouse, because provider can give you some basic uh, stuff like use intelligence tiering, lifecycle configuration, but they will never point your attention to things like, hey, we have 100 terabytes in this folder that are used for no one, so probably you can delete it. So I think that they can provide you some general guidance how you can do this, but the most the crucial benefits you can get only by yourself and knowing how to do this and knowing your particular case and your infrastructure and data warehouse.
Mhm. Yeah, and also you mentioned about changes in infrastructure to decrease costs, but were there any changes in pipelines jobs itself in code?
Yeah, that's also a good topic because ineffective code may also cause extra spending extra resources on computing, but I did not mention it here because it's more connected to a business logic. If analysts using partitioning and other basic stuff, we can think that this layer is fine, and we can dive into more engineering solution. But yeah, the business logic, the code, it's also a way where you can optimize and save the cost also, but it's not covered here. It wasn't covered here.
Mhm. Yeah, you also mentioned how you optimized costs, but yeah, it can bring performance issues. So how was it tested? Did you create like a separate cluster or separate AWS account with all this stuff, or
No.
did
It's
changes live?
yeah. So all changes were applied to the production one, but it wasn't in one step. So it took me about 3 months to apply all the steps that I talk in presentation during this period. So I was moving by very short step, monitoring daily the workload, the ETL, because I didn't want to break anything. So it was like step by step actions, but on the real environment, and it took, as I mentioned, about 3 months. So everything was in a production, but I moved very slow and carefully with all these changes.
Mhm. Okay, yeah. Thank you, Igor, for your presentation. Really interesting. So yeah. It was a presentation how to reduce costs. So I ask you to stay tuned. And next presentation from Alexander, he will share his experience of creating, of using big data with no costs. So this is the next level. So stay tuned. Thank you, Igor.
Bye.